So I'm Scott Anderson. I'm the PI of DIMPLE, Dating an Irregular Mare Patch with a Lunar Explorer. And we're thrilled to have been selected just last Friday to fly this mission to a irregular Mare patch called Ina and land right here on a smooth mound within Ina called Mons Agnes and assess the age of this feature to determine whether the moon was volcanically active in the recent past. And this, of course, is a team effort, and I really want to highlight our incredible team. I'm going to talk about them a little bit more in just a moment. Next slide, please. So why did we target an irregular Mare patch? Obviously, dates are critical for understanding geology and the rate of geologic processes throughout the solar system. And towards that end, I've spent about 2 decades building chronology instruments to try to achieve this. In competition and partnership frequently with the incomparable Barb Cohen, who is also doing this. And we've driven each other forward, I believe, to do fantastic work on dating. Usually I would want to go date basins or Maria or similar broad stratigraphic benchmarks. However, the DIMPLE team over the last year really clarified to me the importance of irregular Mare patches, like Ina, the one we want to fly to. The central mystery of Ina is its scarcity of visible impact craters, suggesting that it's very young, about 33 million years. However, there's an alternate view that macro or micro vesicularity or a volcanic foam of some sort may be absorbing these impact craters and may prevent the retention of them, and that instead Ina is ancient, about 3.7 billion years old. So the 33 million year old perspective was championed by Sarah Braden in about 2014, and Jim Head and Li Chao in 2020, and at other times as well in a series of great papers, championed the idea that it's older and that a volcanic foam or highly vesicular surface may be present. So that's one of the key things we'd like to test. On top of that, irregular Mare patch composition is not that well constrained due to their small size. So if we could do some geochemistry and understand their origins, that would be fantastic as well. And I can't wait for you guys to see these pictures close up. Some of you are going to be very familiar with them, but they have very enigmatic surface textures. And being able to land there on the surface and look at these and understand the geologic context, I think is going to be mind-blowing. So our instrument suite, it turns out we can do dating, we can do geochemistry. If we add in a few cameras, and with the addition of Eclipse rover, I think we can really address this problem well. Finally, I'd like to point out that irregular Mare patches, though they're small, they are numerous. There's about 91 of them, suggesting that there is some widespread process that's going on that may be causing very young lunar volcanism. So if they are indeed young, they may be of larger import in assessing lunar evolution than we think. So the bottom line here is, if Ina is young, the Decadal Survey notes that they form a profound challenge to our understanding of lunar geochemical evolution, since it requires unexpectedly long-lived heat sources in the lunar interior. On the other hand, if Ina is old, our DIMPLE mission will test whether it's rock properties like micro or macro vesicularity that lead to its anomalously young crater retention age. And we'll be able to apply these insights to other locations in the solar system that look similar. Next slide. So this is the team, and one of the things that I'm most excited about is that we have both Jim Head and Sarah Braden on this proposal team, this mission team now. So we bookend the hypotheses, and it's been working really well as a way to define all the questions that we need to address. We also have a fantastic group of engineers at Aerospace and Lockheed Martin who've done really great work, as well as Peter Burtz and the University of Bern team helping us with our mass spec, and a fantastic science team, as you see here, who've been working on these kinds of problems for quite some time. Next slide. All right, so we're going to do a brief review of lunar volcanism and IMPs. As you can see here in this great work from Heisinger in 2011 and Jennifer Witten and Head in 2012, you can see that much of the near side of the surface of the moon appears to show that volcanism was most active 3 to 4 billion years ago. And you can see that in this histogram as well. Now, we do have some samples from younger periods of time, but these are rather limited. But the thing that's really mind-blowing here is that if irregular Mare patches really are less than 100 million years, they're going to be off the charts low on these graphs. Next slide. So I wanted to show you some examples of the distribution of these irregular Mare patches. What you're seeing in the picture on the left is about 70 of the 91 that have been identified. You can see they're inside and outside of the Procolarum creep terrain, but they're all pretty much in Mare. They have dimensions of about 100 meters to 5 kilometers. As you can see in this collection of individual imps shown on the right-hand side, they contain irregular morphologies and textures with optically immature floors having sharp meter scale morphology. And there are very few superposed craters on these, more than 10 meters in diameter. And that's the real shocking thing, the really exciting thing. Next slide. So if we zoom in and take a look at the 3 largest of these irregular Mare patches, Koche 5, Sosigenes, and Ina, shown here on the left-hand side of the image, we can see that they do indeed have these crazy textures and very few craters. Sarah Braden went and counted these craters back in 2014 and did crater size, frequency distribution, age estimates on them. And you can see on the right-hand side that those return dates between roughly 20 million years ago and 60 million years ago. This is shockingly low compared to the era of volcanism on the moon as we know it today. Next slide. So now we're going to zoom into Ina. Ina is the largest of these irregular Mare patches and hence makes for a very easy target for a PRISM mission like the one that we are going to carry out. Ina is located in Lacus Felicitatis. It sits on top of a 22-kilometer wide, 320-meter tall, shallow sloped shield volcano, as you can see on the top right in that topo map in the cross section. It's a 3 by 2 kilometer depression that's about 50 meters deep, in which the surrounding Mare is high. Then there are slightly lower smooth islands with very few craters. And then below that is a volcanic, knobby, high albedo terrain with almost no craters. We intend to land on Mons Agnes, as I mentioned earlier, and you can see a little tiny landing circle, which is where we're intending to go. By the way, in this talk, you'll notice that I call them landing circles because they're not technically ellipses under the PRISM program, which is fine with me. They're nice and tight and they'll fit right on that Mons Agnes. Next slide. Okay, here's a zoom in of Ina. A lot of times people have a hard time visually seeing what this surface texture looks like. So this is an image that's been projected into 3 dimensions with a topography map shown on the right-hand side. And so you can see it's got this just crazy lumpy, bumpy texture, and then this sort of very rough texture in between the smooth, high-standing mounds. So it's just absolutely spectacular. And landing here and being able to look out over this terrain is going to be really amazing. Also note that, as I said in the introduction, that the composition of Ina is poorly constrained due to its small size relative to the pixel size of orbiting measurements. And however, I will note there is some titanium, iron, and plagioclase data that provide some constraints, but what we really want to do is pick up multiple samples down on the surface and obtain geochemistry results from our mass spectrometer. So hopefully get a much better answer than what we're getting from orbit. We'll be able to really ground truth it. So, and in addition, the material properties, whether it's highly vesicular or more, much more solidified kind of basaltic rock, we don't really know. So being able to look at the geologic relationships on the ground is going to be very important. Next slide. So a summary of these observations that I've described is shown over here on the left-hand side, where we have a high standing old Mare surface that appears to be about 3.7 billion years old. Below that, we have the smooth unit, which sort of forms these mounds or very small domes that have very few craters. And that appears to embay the uneven or rough unit that's below that, that has a characteristic of being very optically immature, and it appears to be somewhat blocky. And it could be that this material just is young. It's just young volcanic material of about 33 million years. That's the Braden hypothesis. The alternative model is that Ina is ancient, about 3.7 billion years, and that craters are not retained due to macro and micro vesicularity. What's going on here is that a magmatic foam comes out of a stalled dike underneath this terrain and forms a surface crust that eventually collapses, forming a very rough macrovesicular surface. And then through that, we get these small lava domes and ponds that look much smoother because it's also made out of foam that is a little bit more cohesive. Next slide. So DIMPLE plans to assess the age of the basalts over here with question A1 in the top left, whether they are 3.7 billion years. We give it a little bit of latitude. The youngest ancient basalt that we would sort of consider in this category is delivered by the Chang'e 5 results, so about 1900 million years, but we think it's probably 3.7 billion, or whether it's much younger, 33 million years, and we do that with our Codex Larums. So this is one part of the suite. We need to distinguish about a 930 million year difference in ages at 2 sigma, and we think our instrument will produce about 375 million year precision, so we should be able to knock that out of the park. In addition, we'll use the isotope results for rubidium and strontium, as well as a kind of geochemical composition measure to assess creep involvement. And then we'll use the laser ablation mass spec components of Codex to do geochemical composition, grain size, and vesicularity. So we'll use this to distinguish lithology in the total alkali silica diagram, determine ground truth compositions relative to apollotypes, assess abundance of heat-producing elements, and map the elemental abundance, grain size, and vesicularity at a scale of about 200 microns. We can do this because the elemental abundance LAM system makes maps of the elemental abundance. So if there are large vesicles, we actually can map out where all of those are at roughly a 200 micron scale. Finally, we'll have the cameras on the lander and on the rover. So we'll use those to also look at the grain size and vesicularity of samples, assess the geologic relationships between the smooth mounds and the rough terrain, and look at the nature of the regolith that covers Ina. Next slide. So on the left-hand side, I show a picture of a notional lander, a notional rover, and our DIMPLE suite. In the center, I've broken those out of the background picture to make it a little bit easier to see, but it's essentially the same thing. So we'll have a camera looking down at the base of the lander, and for which an arm can reach down and pick up rocks with a little gripper over a 1.5 square meter sampling area. That arm can bring those samples up to a saw and then present them to the Codex laser ablation mass spec, which does geochemistry, and the additional laser subsystems that allow us to do dating using resonance ionization mass spectrometry, sometimes called LARMs. So you'll see that in here as well. On the side of the gripper, we've got some little fingers that can dig into the ground, so we can actually access the subsurface and assess soil properties to a degree. We have a standard glued on the side of the gripper, shown as a little gold stub here. And in addition, we'll have a rover with a little camera on top of it that can drive around and look over the edge from the top of the smooth mound down to the rough terrain, as well as a little rake that can pick up samples and bring them back to Codex. So we're going to be able to do context imaging, sample imaging, elemental mapping, rubidium strontium dating, roving, digging, raking, and cutting. That's the suite. Next page, please. So our plan is to land at the site labeled A in the figure on the right-hand side and do the rover traverses shown as little blue lines. The areas in red are inaccessible due to the high slopes, and the areas in yellow are also inaccessible to our rover because we'll lose line of sight communication to the lander. But everything else is fair game. So first we plan to pick up just the closest rock we can find. Then we'll drive to the area located at number 1 and in a sort of increasingly, well, we're going to do this series of traverses in an increasingly difficult set of attempts to get rocks and to visit Ina. So at site number 1, we're going to visit a 1-meter crater. Then we're going to head out to site number 2, where there's a boulder, and we'll look to pick up small rocks there and bring it back for dating. Then we'll head out to site number 3, which is an impact crater rim, and we'll also bring back a small rock from there to present to Codex. And then we'll head out to site number 4, where we expect we can actually drive down to the uneven rough terrain that's stratigraphically lower and sample those areas. It takes us about 12 hours to measure a single rock in the nominal scenario. However, if everything goes wrong, it takes 3 tries to pick up the rock, 3 tries to image the rock, 3 tries to cut the rock, for example, then we think it'll take about 57 hours to measure one rock. We've got about 348 hours in the lunar day that will be active. So we should be able to do all of these measurements that we've outlined here, and possibly more if the more nominal scenario plays out. I should also note that we're going to be doing teleoperations, so this is a little bit faster than what you might be used to on Mars. Next slide. Okay, so what are the results going to look like? Well, we're going to definitively assess surface properties and vesicularity by imaging of uncut and cut samples, laser ablation mapping of samples, and by doing camera work to establish the proximal and distal geologic context. And for example, looking at vesicularity, like on this Apollo 17 basalt versus this Apollo 15 basalt. I'm only showing these to give you a sense of the vesicularity changes we might see. I'm not particularly interested in the chemistry or the ages of these rocks. Next slide. We'll also obtain laser ablation mass spectra of elemental abundance, like this LAM spectrum of the creep-rich lunar meteorite SAU 169, shown up here on the upper right. This was acquired by the University of Bern, our partners, using the mass spec we'll use for this instrument. And we'll be able to use that and convert that data into weight abundance oxides and to assess the composition of INA on the total alkali silica diagram, for example, looking to see if it's creepy or perhaps just more straight up basalt. We'll also be able to compare the results with ground truth composition of our ground truth composition with the lunar sample database, for example, over on the lower right, and compare that to the orbital data for INA, which is shown as this little triangle kind of in the center of the image. Next slide, please. We'll also be able to obtain dates like this very young date for Zagami over on the left-hand side that we obtained with this equipment in my lab. Or if it's ancient, perhaps like LAP02205, the lunar meteorite, the age in that case is plus or minus 300 million year precision. And so that will perfectly work for the kinds of problems that we need to solve at INA. Now, obviously, these are a little bit different than what INA may produce for us. But we think this really bookends the kinds of results that we might expect to see. Next slide. We can also use those dates and the intercept from those rubidium strontium isotopes that we measure to place the results from INA in context with, for example, the high alkali sweet granites, or determine whether perhaps INA looks more like creep or perhaps like the bulk moon. In that graph in the upper right. And just using the age, we can assess where INA falls in comparison with all of the Apollo samples. Just as an example, sort of in the 3.9 to 4 billion year old range, it could end up having a date sort of like the Apollo 15 creepy basalts, and maybe a chemistry that's similar. Or maybe it's way off the graph to the right, down at 100 million years or less. That would be very exciting. Next slide. All right, so this is the summary. Sorry, I'm running a little bit long. Young INA presents profound challenges to our understanding of lunar geochemical evolution and requires unexpectedly long-lived heat sources in the lunar interior. On the other hand, if INA isn't young and it's instead ancient, then that might well be explained by observations of micro and macro vesicularity that we'll be able to make, and thereby explain its anomalously young crater retention age. These insights can then be applied to crater counting throughout the solar system, wherever we find terrains that look like these irregular Mare patches. So DIMPLE will solve the central mystery of INA, whether it's young or old, and why, and assess the ground truth composition of INA, place it in lunar context, and finally map and image sample vesicularity, assess geologic context, and determine the nature of the regolith at INA. So that's our plan for DIMPLE. Thank you, everyone, and thanks to the DIMPLE team for doing such an awesome job. I'm so excited to hear your questions and carry out this project.
Thank you, Scott, and congratulations.
Oh,
are there
thank
any
you,
questions?
Deborah.
Are there any questions for Scott in the room? And are there any online? Well, Caleb runs to the mic.
Sure, I'll bite. Scott, first of all, this is very exciting as a mission. I'm really hoping this proves out this technology for us in future missions as well. I should say Caleb Fassett, APL. One thing about INA that I think could happen is that it turns out that the rocks are old and it's not vesicular, in the sense that if craters aren't retained for a different reason, then you could explain both the Braden results and also sort of the context in this older lava flow. So have you thought at all about alternative mechanisms for resetting of the crater population, perhaps like what Pete Schultz presented in Nature in 2006?
So yeah, that's absolutely right. There's actually a handful of different potential hypotheses. And I think the beauty of the instrument suite that we are bringing with us here is that we will be able to assess that date independently of the vesicularity. Now, we've sort of chosen these two end members, what I call end member scenarios, because we really want to understand those geologic relationships as well as get the date. And we're hopeful that the story will end up supporting itself. But it may be that we're driven to one of these other models and in the end. But right now, I guess, so I mean, there's significant debate on the team about which model is correct. And so, I mean, that's the whole point of going here. We want to go find out. And I think we've got the right set of equipment to do it, particularly when we match it with the geochemistry.
Thanks. I think we do have at least one question online.
Question online: will you be able to detect outgassing from INA in situ?
Oh, that's an excellent question. You know, I don't think so. I don't think so. This mass spectrometer is not really optimized to do that. You know, I mean, there's some possibility, but the laser ablation approach is unlikely to create very many ions from the atmosphere, if such as it is. And I don't think we'd be able to distinguish it very well. So unfortunately, I think the answer to that one is no. Though we would love to, but as everyone knows, these missions are very requirements driven, and we kind of have to choose the simplest set of things that we're pretty confident we can do. So I would love to answer yes, but sorry, I don't think so.
Thanks, Scott.
Any other
Are there
questions?
Any other questions online? No. All right. That seems to be it from the room as well, Scott. So thank you so much for joining us today, and congratulations. We look forward to getting Codex down to the moon and DIMPLE to investigate INA and answer all these amazing questions. Thanks very much.
Thank you, Deborah. And also thank you everyone who supported us for so many years.